Hi, everyone. Thank you for joining the second webinar in the American Concrete Institute webinar series, led by Nizar Marjaba. He's the regional manager at Cortec Middle East and an ACI board member. His topic today is Engineered Corrosion Solutions, Protect and Preserve. The last webinar in the webinar series will continue tomorrow at the same time. You will receive an email with a link to access the webinar tomorrow. All the webinars will be recorded and you will receive the recording and the presentations within the next week. If you have any questions, please direct them to the Q&A box at the bottom of your screens and we will answer as many as we can after the presentation. I will now pass you over to Nizar. Hi, Nizar.
Hello, Eleni. Thank you. Thank you for the introduction. And thanks for the Big Five and ACI for giving me the opportunity to to speak at the ACI webinar series this week. But I'll just start off with just to give a quick, for those who don't know me, just to give a quick background on myself. My name is Nizar Marjaba. I graduated in Lebanon civil engineering, followed by a master's engineering management degree in University of Wollongong. I have more than 10 years experience in the GCC, and I'm currently a member of the International Concrete Repair Institute and ACI International. I currently sit on the board of directors at UAE ACI chapter as secretary and treasurer. And as Eleni mentioned, I'm currently Cortec's regional manager based in Dubai. Our agenda will be as follows. We'll start off talking about equipment preservation. Then we'll talk about corrosion inhibitors for new build concrete structures, which come in forms of admixtures for concrete, and we'll be talking about corrosion inhibitors for existing structures that come in multiple forms. Then we'll have some time for Q&A. Now, I know the majority of you are mostly coming from a civil and structural engineering background, so probably most of you are wondering why, how is the first topic of equipment preservation relevant here? As most of you know, probably some of you know about our solutions for durability enhancement in concrete and corrosion protection, but very few know of other technologies and solutions and services that we provide. So I thought I'd share with you, especially during these difficult times, what equipment preservation is really all about. Before we dive in, just to give a quick brief introduction on Cortec. So Cortec Corporation is based, headquartered in USA, Minnesota, with 8 manufacturing facilities and 65 patents. Its mission is to pioneer and lead preservation solutions protecting life, assets, and the environment. So why do we use equipment preservation? What is preservation? Equipment preservation is very important as it has very high impact on budget, which applies throughout the whole assets life cycle. And budget nowadays is a very, very big thing. So before we dive into more details, I'd like to share with you what is the meaning of preservation. Well, basically, there are multiple definitions for preservation. I'll just put it in simple words. It's basically protecting assets when they are out of service. That could be from transport to storage to commissioning. How do equipments look like? They could be it could be a pump, it could be an engine, it could be a bolt, it could be a pipe. So these are basically what equipments look like. And now I'll be sharing with you a couple of examples on projects which experienced and suffered delays, basically mainly due to corrosion. So the top image shows it's a carbon plant in one of the global mega projects, and it actually suffered. It began It began after a 2-year delay, and the main reason was due to valve preservation, due to the valve's corrosion because of lack of proper preservation procedures. The one below is an offshore project in Egypt. Corrosion was discovered during the commissioning, which was delayed, which actually got the project delayed for 12 months, basically. And over here, this is a 9 million metric ton per annum refinery project. Now, the daily delay for this project cost $1.5 million US. So imagine how would it look like when we're talking about months and years of delay. We're talking about hundreds and hundreds of millions of dollars. Going into more details into the equipments, part of these facilities, these are just examples. I'll just be going quickly through them. So these are examples of fan cooler bearings, corroded, multi-stage pump, corroded, compressive valve, corroded, equipment skids. Now this is very interesting here. Equipment skids, the image on the left shows a skid that's been protected with a blue tarpaulin. You all know with the blue covering protective cover. Basically what happened here is it reached the site. It was out there in the yard, exposed to this aggressive environment, and it actually degraded within 2 to 3 weeks, and it became, as you can see in the image. Basically, depending on the UV intensity, leaving the equipment exposed during the storage makes it very, very vulnerable. Now, the picture on the right is also quite interesting, where the skid equipment itself was preserved from manufacturing, and the customs basically tore open the preservation, and it arrived the way we can see it to site, and it laid down, exposing the full equipment skid, just laying out there in the yard, exposed in the aggressive conditions. Other examples of stainless steel internal trays. So a lot of us think that stainless steel does not corrode. Well, this is a 410 graded stainless steel. Because of sandstorm as well, lay down the yard with airborne chlorides, it all resulted to pitting corrosion, where the client basically had to reject the whole lot. And obviously, this led to project delays due to long delivery, lead time, etc. And also in above storage tanks. Now, these are very, very critical applications. We're talking about large scale tanks here. And this is an example where pitting corrosion is observed during hydro testing due to lack of preservation. Now, such large scale tanks, they become subjected to aggressive environment. And a lot of these tanks are mostly located in very aggressive environments, such as ports, terminals. They're all near the sea, basically. And another factor is that hydro testing use seawater, and not only the chlorides are a threat, but it's also the microbial induced corrosion, which is also an issue. So coming to the preservation methods. So basically we have one of the very common traditional methods is the use of nitrogen. But the issue here is that nitrogen implies health hazards. So health hazards means that we really need to take serious considerations into that matter, basically. Now, what is our approach? It's the use of VPCI technology, which stands for Vapor Corrosion Inhibitors technology. This technology has been out there for more than 70 years. They're based out of organic salts. They have partial vapor pressure that allows them to vaporize. and they provide protection in 3 phases, which allows them to be combined with nitrogen and dry air. Now, to make it a little bit clearer, I would like to share with you a video, a short animated video on how this technology actually works. So think of it as an air freshener in your car. Emitters, this is an example of an emitter. So VPCI technologies come in different forms. This one here is in an emitter form, where they are designed to slowly release vapor corrosion inhibitor molecules into the air. So when the molecules come into contact with the metal surface, they form a very thin molecular layer. So basically here the layer effectively inhibits the corrosion on the metal surface by providing air and moisture from coming in contact with the surface. So why do we use VPCI technologies? Bottom line is VPCI has multiple advantages compared to conventional methods. One of the main key advantages is it's very environmentally safe. And so that makes it easy to ship, makes it easy to apply, to store, to handle, and to remove or even dispose. And I talked about the 3-phase protection as well that it provides. And it has multiple delivery mechanisms, and it's a multifunctional technology as well. So what are how do best practices really look like? So basically, in order to achieve the best practice, we need to have an allocated budget. And then we need to develop a plan. So this becomes very challenging in the beginning. And then we need to identify stakeholders with proper management and coordination. And then we need to have very well experienced and trained people to execute these practices. So basically, where do we come in? So we come in as the preservation specialists here, as a third party, and we are required to coordinate with all the other parties, so from manufacturers, from the operators, to designers, to EPC contractors. And then we become part of the management team, developing plans and procedures with industry-proven technologies. We become involved in testing and supervision and training and monitoring and inspection. So to summarize on how assets are being basically preserved. So I'm not sure if you can all see the little images there. So on the second row on the left, we can see like a little bath. So that bath is filled with non-toxic rust removal liquid, where you submerge your assets inside of them. And then we move into the cleaning and neutralization stage, where the assets are cleaned and neutralized by hydrojetting, VCI cleaner and degreaser. And then we provide internal and external surfaces of the equipment with VCI coatings as well. And then finally, assets are covered with shrink wrap film made of VPCI as well, which even provides UV protection for outdoor storage. So we can see that the technology itself, the vapor corrosion inhibitor, comes in different forms in material and shape. So I'll be sharing with you here a couple of success preservation for equipment. So this is an example for a nuclear power plant preserving the water reactor. So basically, the units were cleaned with a degreaser as well. They were filled with VCI powder basically fogged inside. And then finally, for final preservation and 3-year storage exposed, the unit is then shrink wrapped with the VCI film. Then this is also example of preservations for spare rotors. This is an example of preserved gas turbine. And to conclude, this is an example for preservation of tanks. So these tanks have manholes at the top. The way to preserve them is fogging liquid corrosion inhibitor inside the tank through all the different manholes that are available on the top of the tank. And within time, we can actually detect the presence of these corrosion inhibitors by using certain detection kits. As we can see on the left, the strip colors change from blue to red, which shows that the presence of the inhibitor is still there, providing its protection. So that's about it in terms of the VPCI technologies. Now I'll move into the concrete part, where we'll begin with talking about corrosion inhibitors for new structures. Basically, within that section, I'll be going very briefly about corrosion mechanism, and then we'll talk about the history and types of inhibitors. Then we're talking about the testing and service life impact on the structures. So to begin with, the corrosion mechanism is clearly well explained in detail in ACI document 222 R-01, which is the protection of metals in concrete against corrosion. Now, I'm sure you all know what corrosion is and how it happens, but the interesting part here is the figure on the right-hand side showing the relative volumes of iron. So this is basically to show that the volume of rust, how much it can expand inside the concrete on the rebar. It can go up to 7 times almost its original size. So imagine the impact of force inside the concrete on the rebar that allows it to spall and explode where the cover is no longer there, basically. So coming to the history of corrosion inhibitors, actually, corrosion inhibitors have been out there for quite some time, since the 1970s. And the first commercial corrosion inhibitor was developed in 1975, which is the calcium nitride base, the inorganic base corrosion inhibitor. But back then, there were no testing methods to really assess the performance of these inhibitors. In 1992, ASTM developed the first testing method, which is called the G109, to really test the performance of corrosion inhibitors. I'll be talking about that later on in the presentation. Then in 2004, ASTM developed a standard specification for corrosion inhibitors. So basically, in 92, the ASTM developed a test and only a test, but there was no acceptance criteria. That's why they developed in 2004 the ASTM C1582, which has acceptance criteria, which actually qualifies what corrosion inhibitors really should meet in order to qualify as a corrosion inhibitor. Now, in 2004 as well, ASTM developed a quick test method for corrosion testing, which is known as the G180. I'll not be really talking about that. It's a little bit more of a complex testing, but you can see results within 72 hours, and it is also an option within the ASTM C1582. So where do we find corrosion inhibitors basically in the documents? One of them is the ACI 212. I'm sure a lot of you probably know this document. It's a report on chemical admixtures, and it defines what corrosion inhibitors are. And it's also linked to the ACI 222, which we saw earlier on corrosion. Now, as we can see on the extract on the right-hand side, it also relates to the ASTM standard, the specification C1582. And it mentions clearly that a material to be considered a corrosion inhibitor must show reduction in the corrosion rate and the corroded area of bars in the concrete that contain chlorides. And another interesting fact here is that it also mentions that techniques or materials that reduce the actual intrusion of chlorides, while they're being useful, of course, they're not actually corrosion inhibitors. So there's a lot of confusion out there that, okay, so if I have water reduction inside concrete, water permeability reduction, then what's the use of corrosion inhibitor? There are two different technologies. They are separate. Each one has a different function. Otherwise, there will be no corrosion inhibitors developed in the market out there. Other documents, the Concrete Society, CS 163. The Concrete Society is based in the UK. It's an association. There was actually a consortium of municipalities and ministries and top consultants around the world that gathered in Bahrain and came up with this document basically to guide engineers to the design of concrete structures, specifically in the Arabian Peninsula. And it also has quite an exact definition of corrosion inhibiting admixture there. And it's also available in the British Standard and other different Concrete Society reports as well, which, as you can see here, one of them is on concrete durability and the other is on the selection of admixtures for concrete. Now, going back to the guide, the CS 163, it defines special structures as any structure that has a service life in excess of 30 years. Now, I'm sure, especially out here in the region, a lot. I mean, barely anyone designs anything less than 30 years. So, especially in the aggressive environments. And any structure that is exposed to severe environment is also considered a special structure. Now, this guide has recommendations. The first recommendation is to conduct specific durability studies and service life prediction. And the other is implementing the use of additional durability enhancement techniques. So this is an extract of, this is just to give an idea, it guides engineers on which directions to go. If you're designing a normal structure, you go a path, and then if you're designing a special structure, there's a different path that needs to be taken, and you come up with a durability plan. So what are these enhancement techniques? This is also an extract from the guide itself. So it's done through 4 ways. The first option is the electrochemical, the use of corrosion chloride monitoring, provision of cathodic protection, or cathodic protection at the outset. And through the surface of the concrete by using sealers and coatings, with the reinforcement by using corrosion-resistant steel or using no steel at all, which is barely the case. And through admixtures by the use of waterproofing admixtures and corrosion-inhibiting admixtures. So, going back to the ACI 212, to specifically talk about the organic corrosion inhibitor classification, one of them is the amine carboxylates, and they are classified as mixed inhibitors. When we say mixed, means they affect both the anodic and the cathodic portions of the corrosion cell. Now, each amine carboxylate molecule is a dipole, and it has positive and negative charges that are attracted to the anodic and the cathodic portions of the corrosion cell. So what happens is, so the amine carboxylate inhibitor is dosed, it's a liquid-based admixture. It's dosed at a fixed dosage rate, irrelevant of the chloride levels. And it's dosed at the batching plant, basically. And its form of protection is a migration mechanism. So it migrates towards the steel, forming a protective layer on the rebar. We call it a monomolecular layer. And this is what really passivates the steel surface. So basically, its main reaction is with the rebar. It doesn't react within the concrete medium, unlike the inorganic inhibitors that react within the concrete medium. So how's that related to the ASTM C1582? So this is an extract of the document, which is a standard specification for admixtures to inhibit chloride-induced corrosion of reinforcing steel in concrete. And it has, so basically it has requirements. The first requirement is conducting all your physical requirements as per the standards. The compressive strength, flexural strength, freeze and thaw, length change, air content, and setting time. And the second requirement is conducting the corrosion testing, basically, which I mentioned earlier, the G109. The G109 is a standard test method for determining the effects of chemical admixtures on corrosion of embedded steel reinforcement in concrete that is exposed to chloride environments. It's a simple setup. So basically, you have a prism, concrete prism, 2 rebars at the bottom, 1 at the top, with a concrete cover of 25 mm. Now, what happens is that the top surface of the concrete is exposed to chloride solution, as we can see on the left. Now, which allows the concrete basically to drink up all this solution for a period of 2 weeks, as per the standard. Then, after that 2 weeks, we remove this water and we dry it for another period of 2 weeks. So as per the standard, this is basically, we have a cycle of 2 weeks of wetting and 2 weeks of drying, which in reality is actually 1 month. So what happens in each and every cycle? As we can see on the right, the rebars are connected with resistors, and the whole objective basically is to read the corrosion potential using a multimeter or voltmeter, and you take recordings basically at each and every cycle. Now, when do we stop this test? Basically, one of the requirements as per the standard, which is related to the C1582, as they are linked and connected, is when the loss of the rebar cross-sectional area in the unprotected sample is 3 times higher than the loss of the cross-sectional area of the protected sample with the inhibitor, basically. And this is how the graph kind of looks like. So you have the control versus so the control is the unprotected specimen, and the one with the amine carboxylate inhibitor, the green line. And this is how a graph would look like for at each and every cycle, basically. Now, and coming to the service life modeling, so the Life 365 is one of the common tools that are used basically for predicting the service life and life cycle cost of concrete structures that are exposed to chlorides. And this is an example of an outcome of how a model would look like. This is an example for an actual project, actually, that we have that we have made for the client in an exposed in an aggressive exposure. So the mix consisted of it was a triple blend, consisted of 30% fly ash and 5% microsilica, with the water to cement ratio of approximately 0.4. The idea here is to show keeping the diffusion coefficient and the surface chlorides constant. What happens when, as soon as you go with the cover? So basically, obviously, the less you have concrete cover, the more risk your structure is to corrosion, basically. And the more you increase, the better. So this shows the service life without the inhibitor and with the inhibitor. What happens as you grow in size in the cover. And we can see here that it could actually double to triple the service life than without the amine carboxylate inhibitor. So that's quite a brief on corrosion inhibitors for new structures. Now I'll be talking about existing structures, which is also nowadays it's a very big thing. Um, I will start off by talking about the codes and standards that are out there where it can guide engineers basically on the right path and assessment for repair. The most common one is the ACI 562, which is basically the code requirements for assessment, repair, and rehabilitation. And there's also the British standard, which is the EN 1504, which also provides systems for protection and repair of concrete. Now, in the ACI 562, there's a very important item highlighted, which is the anodic ring effect. Because unfortunately, nowadays we see a lot of issues where repairs are done in a very, very unprofessional manner, as in terms of execution, which does really create something we call as the anodic ring effect. It's also known as the halo effect, and it's a special form of metal corrosion in which new corrosion sites develop immediately around the repair areas. So basically, we tend to focus on specific areas for patching and repair, and we tend to forget about the other areas where we have no idea what's happening. And within that document as well, it talks about different strategies and approaches for protection, so which involves cathodic protection and the use of corrosion inhibitors as well. And a very important technical guideline that I'd like to share with you was developed by the ICRI, the International Concrete Repair Institute. And this is a guideline for the use of penetrating surface applied corrosion inhibitors. And the primary purpose of this guide is basically to provide information on surface treatments for corrosion mitigation of reinforced concrete structures. And this information is basically intended to provide guidance and sound judgment by engineers, consultants, and others that are specializing in the repair and restoration industry. So why do we use surface applied corrosion inhibitors in restoration? Well, first of all, is to extend the useful service life. And we want to cut the corrosion rates to 1/5 of what they are. And basically to help reduce the ring anode effect, which I mentioned earlier. And they are very compatible with other materials that come on top of these surface applied inhibitors, such as sealers, coatings, and so on. And how do these surface applied inhibitors work? So basically, they also have almost the same tendency, or let's say the mechanism of protection is very similar to that of the admixture that I mentioned earlier. It has a migrating mechanism. And so the first step is via capillary action. So there's this capillary absorption that takes place. And then we go into vapor diffusion. And then finally, we'll have the ionic attraction onto the rebar. And this is where the physical absorption takes place, where the monomolecular layer forms on the rebar, suppressing the anodic and the cathodic reactions, basically. So as we can see in the image below, that the surface applied is being spread everywhere, evenly across all the area, not only at the patched area. We are actually applying this inhibitor all across to provide proper protection all around the damaged areas. I would also like to share with you other kinds of specialty organic corrosion inhibitors that are out there. So one of them is the converter rust primer. Now, this kind of works like magic here, because now the traditional way, which most of you are all aware of, is basically wherever you are, you have a rusted rebar, you bring in your sandblasting machine, which is a hassle, especially if you were talking about buildings in basements. You bring in your sandblasting machine and you start sandblasting your rebars everywhere. Not only that it could have some negative effects on the rebar, structurally, but it also has health and safety hazards as well. And what happens is that zinc-rich primer is usually applied after the sandblasting. What we do here, in this case, we avoid the use of sandblasting. All you need to do is just keep the rebar slightly, like keep the surface, avoiding any loose rust or materials on the rebar. You directly apply the primer onto the rebar, whether you spray it, you brush it, doesn't matter. And what happens is that it converts the rust. So we need to leave the rust there basically, because it uses the rust to transform it into a passive layer, into a passive form, basically. And that's what basically protects the rebar. And if you wonder that how does that affect on the bonding between the new concrete that you're going to apply on top, there's been tests that's been done showing that there is no effect on the bond effect between the rebar after application and the new concrete that you're willing to apply. And in terms of steel applications as well, there's the other types of organic corrosion inhibitors for preservation of steel. But the way this works is basically using the rebars do not have to be rusted basically. And this has been quite a trend during these difficult times. Unfortunately, there were many projects that were already during ongoing construction, and they had to be placed on hold for some time. So you can't just abandon the project and leave those starter bars lying out there exposed to the environment. So basically, what happens is this liquid-based preservation is applied on the rebars, providing protection for 24 months. So you're shielding your rebars until your construction is to commence, basically. Other forms of specialty products comes for the protection of post-tensioning strands. Now, this is mostly applicable as well, which is very valuable, mostly in bridge and infrastructures. Now, the traditional way for post-tensioning, basically, the strands are bought from the manufacturing stage onto the site. They're just like rebars, basically. A lot of cases, they're mishandled on the site. Quality control becomes a nightmare because these strands are very, very delicate. They're much more delicate than rebars. And one slight mistake in those rebars, in those strands, can cause very, very fatal accidents, basically. So what happens is that once they're installed in the system, they usually come as greased, some oil protection, and then before they apply the grouting into the ducting system, they usually flush the system with some form of liquid. So they are introducing liquid into the system. So unfortunately, like this is an example on the right where we have chalky and segregation in the grout, where the grout does not really hold on to the mix of the flushing materials and the oils that were already present on the strands. And this, in the long term, causes, surprisingly, it can cause severe damages to the strands. So what we do here is that we introduce powder inhibitor into the ducting system, whether it's a segmental bridge, whether it's a full cast-in-place deck, whatever post-tensioning system is available, there's a solution for it to protect your post-tensioning system by fogging the inhibitor. As you can see on the left, you fog the powder inhibitor into the system, calculated based on the volume and the length of the of the duct, and this will basically provide protection for the strands inside the ducting system. And the beauty about this is that you will not really require to apply any types of oils and grease onto these strands. So, and flushing is also not even required. So it goes with, there's been testing done as well, the pull-out test, how showing the compatibility of the inhibitor on the strands with the new grout that's going to be applied. So basically, by that I conclude. Please don't forget, tomorrow the American Concrete Institute webinar series will continue. Tomorrow there will be a presentation delivered by Mr. Salah Abu Abeid on essential knowledge to concrete floor construction. So don't forget to tune in tomorrow, same time. Now we can have some time for questions and answers.
Thank you, Nizar. We have quite a few questions coming into the Q&A box, so I'll just ask them, and I apologize if my pronunciation is a bit off. What is the difference between corrosion inhibitor versus waterproofing admixture?
Okay, good question. I did mention earlier that there's always this confusion that happens. So basically, as I showed in the ACI 212 document, where they obviously clarify that they are two different technologies. Now, corrosion inhibitor, its role is to inhibit corrosion, especially when its reaction is directly with the metal, with the steel. So when we are forming the passive layer on the rebar, we are directly, so this inhibitor is directly reacting with the rebar. Now, having that said, since it's not affecting the concrete medium, what happens when you have cracks? Now, I did not share this information earlier, so that's a good question that's asked. There were also further testings done, basically. So that specimen that I showed you on the ASTM G109, we cracked those samples open in a form of like how it would be, you know, we really wanted to see how would this performance be even when we have cracks versus waterproofing. So we had even mixes with waterproofing where they were also cracked, and because eventually concrete will crack by nature. Whatever you do, concrete will always crack. And in time, you'll always have seepage into the concrete, and eventually everything's going to reach the rebar. So the waterproofing does its actions basically to reduce permeability. It acts as a waterproofer, not allowing the water to penetrate. And the corrosion inhibitor acts as a product to inhibit corrosion, to protect the reinforcement from corrosion. But when you have cracks, you are reducing the efficiency of waterproofing in time, eventually. While you have the corrosion inhibitor on the rebar already protected. So even if you have cracks and the waterproofing somehow in the long run fails or reduces its efficiency, then your steel is still protected, basically. I hope that answers your question.
Another one, which method of corrosion protection for reinforcement bar is most effective?
Which method for protection of
corrosion protection for reinforcement bar is most effective?
Well, basically, there are different forms of protections out there for reinforced concrete structures. So corrosion inhibitors have been introduced for this sole purpose. And one of the most common and oldest methods for protection is the use of cathodic protection as well. So I would probably say cathodic protection and corrosion inhibitors are the most result-oriented in terms of corrosion protection, basically.
Is there any product to give exposed rebars protection from corrosion for 5 years?
That's a little bit difficult to answer. I mean, despite all the lab testing that has been done on spray salts and exposed to salts and assessing the performance of these inhibitors on metals under very extreme harsh conditions, we take it case by case, basically, depending on how severe the environment is, depending on how severe the situation of the rebar is, depending on, I mean, are we talking about a new construction? Are we talking about an old existing structure? So there's a lot of factors here that that play a role here before we come up with such a decision. But for the preservation of the rebars, the most we have seen so far was up to 2 years of protection, basically, and this was actually a real example that we have, basically.
What is the difference between the amine carboxylate and amine ester corrosion inhibitors?
Okay, that's a good question. So in the ACI 212, it does also classify. So amine ester is also an organic base corrosion inhibitor. There are more or less, as I think, as I recall, amine esters are they have waterproofing properties as well that they're provided at a higher dosage rate than the amine carboxylate inhibitors. But they're both classified as in the ACI 212 as organic corrosion inhibitors, basically.
Is it possible to replace the cathodic protection system with corrosion inhibitors?
Well, that would also depend on the situation, depending on the scale of the project, depending on the service life required for the project. Amine carboxylate inhibitor and cathodic protection provide the same result as, which is basically corrosion protection. They do work kind of different. So there are several ways to approach this. One is basically provide provisional cathodic protection while at the same time using corrosion inhibitor in the concrete mix. That way, the client would not have to really spend the full lot in the very beginning, you know, on the execution of the full cathodic protection system, turning on the cathodic protection system. And there are some cases that cathodic protection is not really required when inhibitors are present in the concrete.
Will corrosion inhibitors have any effect on concrete workability and any effect like slump loss?
No, the only effect that amine carboxylates have on the concrete mix is the slight delay in setting time. It's known to act as a retarder, which is quite a positive thing in our region here. Other than that, testings have showed that they can actually provide 5 to 10% increase in strength for the 28 days results, where the 7 days showed absolutely no change compared to the normal specimens of the same mix, basically. Other than that, it absolutely has no effect on the other concrete properties, especially having a very, very fixed and low dosage rate in the concrete mix.
For new structures, the migration of your product towards the reinforcement happens during the concrete set time or continues during the lifetime of concrete?
Sorry, can you repeat that?
For new structures, the migration of your product towards the reinforcement happens during concrete set time or continues during the lifetime of concrete?
No, it continues. Basically, it continues. Once the concrete is poured, and immediately the migration mechanism begins. And once they reach to the rebar, the layer stays actually protecting throughout the cycle.
How do you account for soil and water chemical content in the 365 design life model?
How do we account for the soil
and water chemical content in the 365 design life model?
Well, basically in the design model, what happens is that we take all the certain parameters of the mixed design and the soil report. So we input all the data on whether it's chloride levels and the type of exposure, where all based on the soil report basically, and we input all that data in, including the mixed design, the concrete cover, and then we generate the results of the report.
Is there a procedure in the ASTM for rebar corrosion prevention?
Okay, I'm not sure I understand that question. Rebar corrosion prevention.
Is there a procedure?
Well, I did mention about the ASTM standards that are available for testing procedures, linking them with the specification. And this is how to evaluate basically the performance of corrosion inhibitors, which eventually results in how you efficiently protect your rebar from corrosion.
Okay. Are you aware of any studies where the chemical composition of corrosion inhibitors have an effect on the mechanical properties of alkali activated concrete?
Okay, that's a long question. I'm trying to see, open the
Q&A bar?
Yeah.
Oh, it's a bit further down. We have a lot of questions.
Okay.
So are you aware of any study where chemical composition of corrosion inhibitors have an effect on mechanical properties of alkali activated concrete?
Not that I know of, but I could definitely.
Maybe this contact could email you.
Yeah, definitely. I'm sure we have something regarding that.
Okay.
I could share that with you whatever I find.
Okay. Is there any method for repairing the corroded rebars in an existing structure?
Yes, it's those methods that I mentioned in terms of corroded rebar applications, which one of them is the so if it's a corroded rebar, basically the right way would be the application of the rust converter. So all you need to do is expose the rebar, apply the rust converter onto the rebar, allowing it to take for the converter to transform the rust into a passive layer, and then you just patch up to the concrete, and then you'll apply the surface applied inhibitor on the surface of the concrete.
If a bar for some reason didn't get protection migrate to it on a small portion, will there be a multiplied corrosion at this area, similar to what happens with epoxy coated bars?
So are we talking about, okay, maybe you won't be able to answer.
Probably not.
So, okay, so if we're talking about new build, like for new concrete, basically think of it this way: as already the inhibitor is being mixed within the concrete mix, and this paste, this mix, is going to be poured all over the concrete, all over the rebars, whether it's a raft, foundation, wall, and all the rebars are basically going to be covered with this paste, and all these pastes consist of the inhibitors which are contained into in the mix. So I'm not sure that would be applicable for new concrete. That's why we highly advise in the earlier stage, protect your concrete from the very beginning. Now, for existing concrete, there are some cases where it might be challenging, I don't know, depending on location of the structure or whatever areas that we are protecting with the inhibitor. We highly recommend it to be applied all around the surface. Does it create pitting corrosion in areas where it will not? It really depends on where that location really is. How far is it from the last area where the inhibitor has been applied? So that's kind of a vague. I'll prefer a one-to-one conversation to understand more on that.
Will any of the corrosion inhibitors introduced affect the bond between concrete and steel?
No, absolutely. There's been a lot of testings done regarding bond tests, and they all showed no effect between the new concrete and the applied material on the surface. So no, there's no effect on the bond.
Okay, I think we'll have time for one more.
Okay.
We have many questions. How do you compare the performance of steel epoxy coating to corrosion inhibitor?
That's a good question. Now, epoxy steel is basically so we all know its main limitations are basically the quality control nightmare. Controlling the quality on epoxy rebars. Now in lab, in theory, epoxy does its job. It protects your steel from corrosion. But on construction sites, it's a nightmare. And what happens with epoxy, as you may know, if you have a little scratch on one rebar, you have just actually jeopardized your whole system of protection. Basically, it starts spreading underneath the coating like cancer. The rust starts to form underneath the coating. Pitting corrosion forms, and then you'll end up having catastrophe results. You would have been better off with a black steel that is corroded than an epoxy rebar that's corroded, basically. Now, not to mention the service life. When we talk about epoxy steel that serves the service life of structures, it also has limitations. I haven't seen, I mean, as per researches and studies, more than 20 years of service life, epoxy does not provide epoxy steel protection. Whereas with MCI, with the corrosion inhibitors, it's different. It's easy to use. It's environmentally safe, and it's a fixed dosage rate, low dosage rate at the batching plant, and it does its protection in the concrete, basically.
Okay, great. We do have a lot of questions. So Nizar, I'm sure you wouldn't mind if anyone wanted to email you if they needed some more information.
Definitely.
Because we are running out of time. But
okay,
thank
so
you.
my email is there mentioned. So feel free to contact me anytime.
Great. Thank you, Nizar, so much for presenting today.
Thank you, Eleni, and thank you all. Thank you all for attending.
Thank you to the attendees too. We are recording the session, all of the sessions, yesterday's session, today's session, and tomorrow's session. So everyone will receive the recording next week. And just a reminder to attend the session tomorrow. So thank you so much, Nizar, for your time today.
Thank you.
Goodbye, everyone.
Take care. Bye-bye.